So today we'll be doing a recapitulation. Right now we know, so we are basically studying our nucleus, and we know that it is a quite unique quantum system. In which sense? Unique quantum system. Now, in which sense is it unique? Well, of course, the first thing is that there are two types of fermions which exist inside the nucleus. The next is that the nucleons in it are not too few to be treated exactly, but also not too large to be treated statistically. So neither exact, although right now today as of 2021 exact calculations are being done, but it is still not possible to do the calculations for all of them. Very few nuclei has been possible, and also neither exact nor statistical. Now for statistical calculations you need a very large number, but here the number is very small, around 300. So in this case we are facing great deal of challenges, right? So what is our approach? Now you see mesons, let's talk about them. You see, mesons are field quanta exchange between nucleons. Okay, when they interact with each other. However, we know that both nucleons and mesons are not fundamental particles. Just a second. Yeah, are not fundamental particles, right? So what are the fundamental particles? Basically quarks and gluons. But you see, gaining an understanding of nuclear physics using quarks and gluons as a starting point. So basically the starting point of study should be, why is this happening, of study, it should be basically gaining understanding of nucleus in terms of quarks plus gluons. But right now it is still not possible. Now while we shall attempt where relevant to make connections with the underlying quark structure, we shall think of nuclei primarily in terms of nucleons and mesons. Now there is a very important reason. So basically instead of this approach, what we will do, we will think of nucleus in terms of primarily this one, mesons plus nucleons. And there is a very important reason, because you see the effects of quarks have not been noticed in conventional measurements. The effects of quarks plus gluons in conventional nuclear physics experiments have not been observed. Okay, and so we can explain, and so we can explain all of nuclear physics in terms of nucleons and plus mesons. Fine. So with this, let us now start. Okay, so the first thing I am going to tell you is that let us say, let us try to play God, and let us just theoretically try to create nuclei. So with one nucleon we have a basically just one nucleon only, single nucleon. What if we have got two nucleons together? Now you already know two nucleon system. Now there are three possibilities, right? NN, NP and PP. But we know from our experience that only this is stable, this exists, and these two are not. Well, this very fact of the existence of deuteron tells us huge information about the interaction, right, about the nuclear force. Okay. And also, not all the states are stable, only the ground state is there in deuteron. Now, as we keep on increasing and so on and so forth, we will have more and more nuclei and so on and so forth. And so we get the nuclear chart with approximately 3000 nuclei. Okay. Now it is very common understanding that whenever we try to talk about something or whenever we try to compare two things, we always try to first ask which one is stronger, which one is stable, something like that. Okay, so again, for all these nuclei here, all of them around 3000 nuclei, the same thing comes to our mind. Which of them are more strongly bound? These are nuclei, bound systems, right? Bound by your strong interaction, which is keeping them together. Okay, now which are the most strongly bound ones? So strong, or you see strength comparison. Now how do we do that? So what we do is that for all nuclei, how do we do this strength comparison? You see, there are two ways of doing so. Very basic. One is, you see, it's the energy of the first few excited state. Energies of first few excited states. Again, there is single nucleon removal energy, and there is one very important comparison parameter. Don't forget it. Remember what is that? It is basically the binding energy per nucleon. When you do this per nucleon, then basically we are trying to compare all the nuclei together, and you know the result. If this is mass, if this is binding energy per nucleon, then we know the result, right? So this is around iron 56 iron, which is most strongly bound, and after that the Coulomb effect becomes important. So electromagnetic interaction starts playing a huge role, the Coulomb repulsion basically between the protons, and as a result we have lower binding energy than your, this peak is around at 8.5 MeV per nucleon. Anyway, So this we know, all these things. But these two, I think you have, this also you know, this measure of strength, which is single nucleon removal energies, single proton, single nucleon, okay, separation energies, basically, for neutron and proton. And this is very important, energies of the first few excited states. Okay, so let's proceed forward. Okay, so what I have been saying right now is the following. Basically, if there are two systems with different number of nucleon, then the system with, you see, greater binding energy per nucleon, for the case of the nucleus, who is stronger is the one with the greater binding energy per nucleon. So, out of two systems, say A, no, not, I will not route A, say there are two nucleons, there are two nucleus, say X and Y. They have different protons and neutrons, and it is observed that the binding energy per nucleon of X is greater than Y. Then I will say that X is much more strongly bound compared to Y. Right? And you see this observation which I just showed it to you. You see, this is basically the first, one of the greatest observations in nuclear physics. This is very important. This tells us a lot. It tells us if we take all the nucleons together, then which one of them are more stronger than others, or more strongly bound. And what about the next greatest observation? Basically, it is related to these ones. So you see, the next greatest observation, the second greatest observation, is the observations of magic numbers. Okay, now it is observed that nuclei with Z is equal to 2, 8, 20, 40, 82, and N is equal to how much? Again, 2, 8, 20, 50, 82, 126. They are special. Why? As for them, the binding energy is higher than, per nucleon, is higher than the neighboring nuclei. Okay. Now these properties are prominent, and so these are known as magic numbers. Now you have learned about magic numbers in your graduations and all that, and we know how to explain this. So these magic numbers, they can be explained by independent particle model, where the effect of all other nucleons in the system is in the nucleus is replaced by an average or mean field which binds the individual nucleons to the nucleus. So now with this, I will now give you very basic ideas about the mean field concept. So basically we are talking about the atomic nucleus, right, with A nucleons, N proton, N neutrons, Z protons. Fine. And this is basically a complex many body quantum system. not exactly solvable. Okay, so what to do? So our way out is use of approximate schemes. This is what we always do as a physicists. And you see, there are many approximate schemes, and one of the most successful is your mean field. So this is what we will talk about now. Fine. Now you see, in non-relativistic framework, let us solve this A body Schrödinger equation for A nucleons, right, with a simple two-body interaction. So let me write H psi lambda is equal to summation over I H cross square by twice of mi Li square plus, this is kinetic, this is your potential term or two-body interaction term, right? And this is equal to E psi lambda. Now remember, here basically we are doing an approximation. Okay, and what is that? We are assuming, basically, you see, if we have a nucleus with many nucleons, then there can be interactions between all of them together. So we can have terms like two body, like three body, four body, and all that. But what we are assuming in the real world, in the real case, they are not, all of them are there. Two body, three body, four body interactions are there. Although the effect of three body is quite small, it has been observed, but it is there. But what we are doing, in the most simplest case, we are just considering this two body interaction. You see over here, and we are just neglecting these higher interactions. You must remember. Okay, now what we are going to do is look at the very nature of this two structure. So I'll just do a little bit mathematics and then discuss the consequences. So what I'm going to do is I'm going to add and subtract, add and subtract a one body term, say OI, which acts on ith nucleon. So then our Hamiltonian can be written as summation over I minus H cross square by twice of mi del I square plus OI plus, you see what I am doing? So basically you can think, now you understand what I am trying to do. Basically my aim is to take care of this. So I want to treat this, you can think, as if in the quantum system I would like to take this term together out and treat it separately, maybe if possible as a perturbation also. Okay. Okay, now let me say that this is your HO acting on the ith nucleon, and this is your HI. Okay, so my entire Hamiltonian we have written in terms of summation over I HOI plus your HI. Okay. Now this is basically the one body part for the ith nucleon. So if we do the summation, then we will get HO plus HI. Now this is basically the mean field, and this is your two body minus one body turn, or basically this is the leftover interaction. Also, this is sometimes known as residual interaction. Now I told you previously that we will be trying to solve this quantum system, many-body quantum system, using various approximation schemes. So till now, only approximation I have done is regarding taking the two-body interaction only. The next now, which is basically the most important one, is the independent particle picture. Remember, which we discussed during your magic numbers. So you can say that this is basically the one of the most important approximations. So our approximation is, let us choose OI, the one body term, in such a way so as to make HI as small as possible. You see what I am trying to do? Quantum mechanics problems. I would like to make this additional term as small as possible, if it is so, and then we can treat it as perturbation. Then you see, HI can be ignored. If it is very small, just forget it, that it was there. And what if we can ignore it? That's the best possible outcome, right? HI can be ignored. So then HI can be ignored, and all the nucleons, all the nucleons move independently with the mean field H0, and this leads to independent particle picture. Okay, now regarding HO, you see HO, it can be calculated microscopically. Starting from your nucleon interaction. Okay, or there is another way. It is phenomenological. So basically we put by hand a form of potential which you are very comfortable with, right? Say for example harmonic oscillator, and this gives us spherical shell model. Not only harmonic oscillator, we can also have Woods action potential, right? So basically this gives us a spherical shell model, and also we can have, you see, deformed shell model. So basically we can have different choice of this mean field potentials, we can have wood section, we can have harmonic oscillator. Okay, so, and if we include deformations, then we have deformed shell models. Now, before I proceed further, we are facing, you have to understand that we are facing a very basic fundamental puzzle. And what is that fundamental puzzle? And what puzzle is that? You see, the nucleons, they interact strongly. Fine. So how is it possible for them to move independently without collisions in the mean field potential? You must be thinking about this. How is it so? Now, you see, the answer comes from the Pauli spin statistics theorem. Which basically requires that nucleons with spin half are B fermions, right? And so the many body wave function, this means that the many body wave function, it must be antisymmetric under particle exchange. Now this antisymmetry, this basically, it produces a pair correlation function which keeps the nucleons apart. Okay, now what is pair correlation function? Basically, in statistical mechanics, pair correlation function in a system of particles basically describes how density varies as a function of the distance from a reference particle. Okay, now the result is this. So here the number is 1. So this is basically pair correlation function which I am doing a plot, and so this is some f lambda lambda as a function of x, and this x is your kf into r, and the values are 2, 4, 6, 8 and so on and so forth. Now you see the result is something like this. It saturates at 1 here, and this kf, its value is basically 1.36 Fermi meter inverse. So what is the Fermi momentum? The Fermi momentum, you see F is for Fermi. Fermi momentum PF is basically H cross into KF. Okay, so you see the nature over here of this pair correlation function. So the value where it saturates starts saturating, you see. So basically the average distance between nucleons in a nucleus, so we can say from here that average distance between nucleons in a nucleus is about 2.4 Fermi meter. Now we do know that at large distances the nucleon potential is relatively weak. Okay, so this is how basically this fundamental puzzle has been resolved using Pauli's exclusion principle, in a way you can say. Fine, so let me again talk about a little bit here. Okay, so you see what I have been saying till now, mostly stressing to the point that partly because of the complexity of the quantum many body system, our model construction is a essential step. Otherwise, we will never have a proper understanding of the atomic nucleus. Now, here in the spherical shell model, what we basically do is the OI, you remember in the first term we introduced the OI term here, you see, not this one, after that here you see this OI term, single body potential, yes, here. So what we do in this spherical shell model potential is basically we choose the spherical oscillator potential. So we choose OI as half m omega square r square along with the spin dot s interaction alpha L dot s. So this is what we do in the spherical shell model potential, spherical shell model. Similarly, in the deformed shell model, I will talk about when I discuss this, there is a modification of this, but again L dot S interaction is there. Okay, so let's do a quick mathematical recap. So what we have done is basically this. We have set up this equation. This is equation 1, where this Hamiltonian H is equal to H0 mean field plus the residual interaction. Equation 2. Now we have been talking in terms of H only. Now let us give importance to this H0 now. So let H0 into phi lambda is equal to epsilon lambda into phi lambda. So instead of now working with the entire Hamiltonian, we are now working with the mean field. Okay, so from this step onwards, basically we now work on mean field, and let's see what happens. Okay, so from this step onwards so basically the introduction of this one body term, it has enabled to define basis functions phi lambda of this unperturbed Hamiltonian H0, so that for each nucleon, now this is for the entire mean field, so all the nucleons, now for each nucleon what we have is this minus let me say this is number 3. So for each nucleon we have minus h cross square by twice m del square plus u into phi k is equal to ek into phi k. So this is what I am saying. Basically I am introducing a potential u which has enabled to define this basis wave function phi lambda of this unperturbed Hamiltonian, and this is for each nucleon. This is for each nucleon, this wave function. Okay, now here this phi lambda, these are basically anti-symmetrized product of a single particle states phi k which are occupied by which are occupied by A nucleons. Following Pauli principle. Okay, and also here, and also along with this we have this relation that is equal to summation over k ek, right? So sum over occupied states. Now you see this phi k, they form an infinite set. Right, and any arrangement of A nucleons occupying different states phi k, just a second, why is it changing? Different states phi k will give us 1 phi lambda. So what are we going to do is, so we have talked about the antisymmetrized products now, and we have talked about this arrangement. It will give us, how it will give us, each arrangement will give us 1 phi lambda. Now let us solve this equation 4. Let us try to solve this. Now here, okay, so you see solution of equation 4, it gives us complete set of phi lambda and E lambda. So let me write it down. Mu phi lambda. Now this is the mathematical statement. This is the mathematical statement of configuration mixing. And A lambda mu are configuration mixing coefficients. This I will talk about later on. When I talk about 18 oxygen, I will explain to you. I will again come back here as well at that time. Now, if we substitute this in equation 1, then you see what we get is the following. A lambda mu into epsilon mu delta mu plus phi nu into hi Now you see this is basically your H mu nu. So let me again show you the equation 1. Yes, so this is what the substitution in equation 1 is giving us. Now this is your H mu nu, and the eigenvalues and eigenfunctions of this matrix H mu nu, it will give us the energies E lambda and corresponding eigenvector A lambda mu. Okay, so far so good. However, you have to understand that we have a big problem yet again. And what is that? The problem is that this H mu nu is infinite dimensional. Okay, and so what does this mean? This means that complete solution is impossible. But we are going to solve this. How? That's the trick. So our solution to this problem is that we have to make proper, valid and useful truncations of this matrix H mu nu. So that one can obtain reasonable results. Which can be compared. Well, you do calculate something which you cannot compare with experiment. That it just goes into vain. How are you going to say that your model is good enough? You must predict something from your model which will be directly comparable with experiment, right? So, which can be compared with observed data. Fine. Now, you see, the first and most drastic truncation. What is it? The first and most drastic truncation? You know, the truncation is we choose U such that H1 it reduces to 0. That means residual interaction, just forget about it. And this is basically the independent particle shell model. Okay. Fine. Now, before I finish, let me talk little bit about the spherical shell model. But again, very basic ideas. So basically, we have got, pardon my handwriting. Okay, here. So, what happens in the spherical shell model is that two things. Number one, all nucleons, they move in one body potential independently, right? And the second thing is that we have got two separate potentials for neutrons and protons. So nu and pi, this is how we denote them, right? Now, if we consider an infinite harmonic oscillator potential, say, let's choose this, UR is equal to half mu omega 0 square R square, then this energy eigenstates, this is just n plus 3 by 2 to H cos omega 0. So these are the energy of the degenerate states belonging to the shell n. Shell n. Now, for each measure shell, basically, each measure shell is characterized by capital M, which is basically the oscillator quanta. Okay, now for each of the major shell, for each major shell, what are the allowed values of orbital angular momentum? What is it? They are basically L is equal to n, n minus 2, so on up to 1 or 0. Now, since you see each nucleon has an intrinsic spin s is equal to half, so the maximum number of neutron or proton that can be accommodated in a harmonic oscillator shell. What is this? This is basically dn is equal to twice into allowed L summation 2L plus 1, and this is just equal to twice into summation k is equal to 1 to n plus 1 k, and this is equal to n plus 1 n plus 1 into n plus 2. Okay, now so what's the value of d0? d0 is 2, d1 is 6, d2 is 12, d3 is 20, and so on and so forth. So you see just a second, yeah. So the total number of states up to some maximum harmonic oscillator quanta, how much is it? It is basically d0 max is equal to 2, d1 max is equal to 2 plus 6, just we did previously, d2 max. You see what we are doing? We are trying to find the harmonic, magic numbers, if we can explain also, is equal to 20, and so on and so forth. Now you will see that what is d3 max? This is also 2 plus 6 plus 12 plus 20, and this is 40. However, d4 max, you will see that the value is 70, and we have a problem. Why? Because we are observing deviations from dn max with k is greater than 0, greater than 4. This doesn't match with the experimental magic numbers. Okay, so what's the solution? The solution is the solution is to bunch the levels. Now how are we going to do that? So we bunch the levels using the L dot S interaction which was introduced. So now we write r square plus alpha L dot S, right? And the energy due to this interaction you can write is n plus 3 by 2 h cross omega plus half alpha L for j is equal to L plus half, and this is equal to minus half alpha L plus 1 for j is equal to L minus half. Now you see what we do is alpha, it is adjusted so that the experimental magic numbers are reproduced. So that's the whole picture. So you see from the picture of the independent particle model, the magic numbers arise because of the fact that the single particle spectrum is grouped into shells with relatively large energy gaps between the shell. So we are basically explaining the magic numbers. Magic numbers. So explaining. So from the picture of the cell model, you can say that these magic numbers, they arise because of fact that single particle spectrum is grouped into shells with relatively large energy gaps between shells. Okay. So we have given a very basic gist of the ideas. Also, I have not proved this, but it can also be shown that this oscillator frequency, it is given by this value 41 by a to the power 1/3 MeV, and this is assuming constant density, sphere model. Okay, so we have talked about the spherical shell model. So what about the success of this spherical shell model? Now you see, all magic numbers are correctly reproduced. So it's a huge success. Great. What about the, are there more? Of course. Now you see, nuclei with closed shells are correctly predicted to have spin 0 and positive parity in ground state. Wow, this is also very good. Are there more? Of course. Now you see, for nuclei with one nucleon outside a closed shell, just a second, outside a closed shell, or which is deficit by one nucleon for its completion, the basically ground state of nucleus. For those cases, the ground state of the nucleus has the spin and parity of the nucleon, and this is just as predicted correctly by shell model. So we have got great success, but that's not all. We cannot explain all the data. Now what are they? So criticisms of spherical shell model. Now you see, the first is that we cannot predict the spin and parity of excited states. Excited states. Okay. Also, we cannot predict the magnetic moment of excited states. And this I will talk about later on, how to deal with this. Basically, you have some idea. The reasons are, number one, the truncation, basically the truncation, where we have not taken into account the residual interaction. Also in the truncation, these things we can predict through core polarization. Again, I will talk about it in the later classes. So you can say that the spherical shell model gives us an oversimplified picture of the actual situation inside the nucleus. Now, the assumption of spherical symmetric potential is incorrect in most of the cases, you know, and this is evidenced by the appreciable quadrupole moment possessed by some of the nuclear states. And we will talk about how to deal with this when I discuss the deformed cases, or basically corrective model. Okay.